Pythagoras theorem is by far the most important concept not only in triangles but also in the entire field of mathematics. To understand it, all we need to do is draw a right triangle. It is a triangle in which one angle is a right angle. What's so special about this triangle or this theorem? The first thing we need to understand is what the side opposite to the right angle is called. It's called the hypotenuse. The Pythagoras theorem says that the hypotenuse has a special relation with the other two sides. It tells us that the square of this length, that is the hypotenuse squared, is equal to the sum of the squares of the other two sides. Remember, it holds true only in the case of a right triangle. So the theorem says that for any right triangle, the square of the hypotenuse is equal to the sum of the squares of the other two sides. Let's say the lengths of the sides are A, B and C. C is the length of the hypotenuse. For this triangle, we can say that C squared is equal to A squared plus B squared. If this is a right angle triangle, the square of this length will always equal the sum of the squares of each of these lengths. This theorem has innumerable uses, so let's look at one in this video. Zara wanted to build a ramp leading from the ground to the back porch. The porch is 3 feet off the ground, and due to building regulations, the ramp must start 7 feet away from the base of the porch. How long will the ramp be? Using the Pythagoras theorem, we can say that the square of the length of this ramp will equal 3 squared plus 7 squared. The square root of this sum will give us the length of the ramp. In the previous video, we saw that if we have a right angle triangle like this, with sides A, B and C, then the Pythagoras theorem says that C squared will equal A squared plus B squared. Let's move on to a new page to understand why. The process to understand the Pythagoras theorem is pretty similar to the one for A plus B the whole squared. We draw a line of any length and mark a point on it. This point can be marked anywhere on the line. We name the parts A and B. This length will be A plus B. Next, we complete the square with A plus B as its side. This is a square in which each length is A plus B. Now we try to make the same division on each segment. We mark points here, here and here. The points should be marked such that this length is B, this length is A, this is B, this is A, and these two lengths are also equal to B and A. We can see that we have 4 points, one on each side. This time, we join the adjacent points. If you draw this on a piece of paper, you will notice that the figure formed inside is a square. Let the length of the sides be C centimeters. Look at the different parts that are formed. The outer square is made up of 5 parts. This square of side C centimeters in between and 4 right angle triangles with height A and base B. Let's zoom out a bit and try to find the area of the outer square. The area of the square can be calculated in 2 ways. The first way is side multiplied by side. It can be written as A plus B multiplied by A plus B, which equals A plus B the whole squared. And the area of the outer square also equals the sum of the areas of these 5 parts. The area of this square is C squared. Observe that each of these triangles will have the same area as their height and base is the same. Area of each triangle is half AB. To include the area of 4 triangles, we just multiply this with 4. Their total area would be 4 multiplied by half AB. 2 times 2 is 4 and we get the area of the outer square as c squared plus 2ab. Both these are the area of the outer square. Equating these two, we can write c squared plus 2ab equals a plus b the whole squared. And using the identity for a plus b the whole squared, we write this as c squared plus 2ab equals a squared plus 2ab plus b squared. And cancelling out 2ab from both the sides, we get c squared equal to a squared plus b squared. This is the Pythagoras theorem. The Pythagoras theorem can be proved in many ways, and we have already seen one previously. Here, let's look at another way in which we can prove it. It's relatively easy. Let's draw a square with the length of all its sides equal to c units. Now we need to construct a triangle with side c as the hypotenuse. So we draw these two lines perpendicular to each other. This becomes a right triangle with this as the hypotenuse. Let the length of this side be a and that of this side be b. We need to prove that a squared plus b squared equals c squared. As this is a square, the length of this side will also be c. Now let's complete this right triangle. This length will be a units, this will be b units. In a similar way, let us complete this triangle. This will be a right triangle with sides A, B and C. Drawing this line gives us another right angle triangle with sides A, B and C. In each of the triangles, the side with length C is the hypotenuse. What we should be interested in finding is the area of the larger square. If you look at the figure carefully, you will notice that what we have in the middle is another square with lengths of sides a minus b. This length is a and this one is b, which is why this will be a minus b. In a similar way, each of the other sides of this quadrilateral will also be equal to a minus b. But what we are interested in finding is the area of the larger square. Zara and Zen were discussing about how they can find the area of the larger square. Zara says that the area of any square equals side multiplied by side. So she writes the area as c times c, which equals c squared. Zen does not use the formula, but instead thinks of a different way to find the area of this square. He says that the area of the larger square will equal the area of the 5 figures formed within the square, 4 of which are triangles and 1 square. So the area of the larger square will be equal to the area of the 4 triangles plus the area of the smaller square formed in the center. First, let's look at the triangles. Each of the triangles has their height as a units and their base as b units. So we can write the total area of the 4 triangles as 4 times half AB. But what is the area of the smaller square formed in the center? As the length of each of its sides is a minus b, its area will be a minus b the whole squared. All we need to do now is work this out. 4 times half AB will equal 2AB, and using the identity, we can write this as a squared minus 2AB plus b squared. 2AB and minus 2AB cancel out, and what we get on the right hand side is a squared plus b squared. We're talking about the area of the same square. So we can say c squared equals a squared plus b squared. So if we have a right triangle with sides a and b and hypotenuse c, then the Pythagoras theorem says that c squared will equal a squared plus b squared. We have seen a few methods in which we can prove the Pythagoras theorem. Here, let's look at an even simpler way to understand it. The theorem is simple. If we have a right triangle with hypotenuse C and sides A and B, A squared plus B squared will equal C squared. Doesn't matter how this triangle is drawn as long as this angle is a right angle. To prove this, let's draw a square with the hypotenuse as the side. These three sides will also have C as their length. The area of this square will be C squared. With this done, let us complete the bigger outer square. This will be B and this will be A. B and A and B and A. Again, doesn't matter how we draw this. The red portion should be a square and this angle should be a right angle. We have four right triangles here with the same area. Let's move this slightly to the left and let's duplicate it on the right. As they are duplicates, their areas will be equal. You can see that each of the figures has four triangles and one square. All the triangles are equal to each other as their base and height are the same. Now focus well. In the figure on our right, let us shuffle the triangles around. Let this triangle drop and stick to this one. Let's move them up. And let this one drop on the triangle at the bottom. We did nothing extraordinary. We're just moving the triangles around. As these lengths are B, the lengths of each of these four sides will be B. Therefore, this is a square with side B. And in the same way, this is a square with side A. The areas of these two squares will be A squared and B squared. Don't forget, the areas of both figures are still equal. Now let me ask you a very simple question. If I remove one triangle from each figure, will the areas of the new figure still be equal? Of course, yes. If we remove the same quantity from two equal sides, the sides will still be equal. So I remove one triangle from each figure. The areas of these two figures will be same. Let's do that one more time. We drop these two triangles. The areas are still equal. Again, we drop these two and then these two. The two figures are still equal as we remove the same quantities from each side. And that is why C squared will equal A squared plus B squared. Interesting, wasn't it? Okay, here's another way to quickly understand the Pythagoras theorem. Let's assume we have square tanks drawn on each side of the right triangle, and the tanks linked to these two sides are filled completely with water. The tank linked with the hypotenuse is empty. If we rotate this circle around the center, the water from these two tanks will get emptied into the tank linked with the hypotenuse, assuming the thickness of the tanks is the same. The volume of water contained in the two smaller tanks will equal the volume of water contained in this big tank. Let us just look at the formula. C squared is equal to A squared plus B squared. This holds true in a right triangle with sides A, B and C, where C is the hypotenuse. This is called the Pythagoras theorem. Let's try out something interesting. We look at different combinations of numbers which satisfy this formula. We can say 5 squared is equal to 3 squared plus 4 squared. 5 squared is 25 and it is equal to 9 plus 16. Another example would be 13 squared is equal to 5 squared plus 12 squared. 169 is equal to 25 plus 144. Or we can also say that 10 squared is 6 squared plus 8 squared. 100 is equal to 36 plus 64. This means we can form right triangles with sides 5, 3 and 4, in which 5 is the hypotenuse. And similarly, in the second and the third case, we can form right triangles with hypotenuse 13 and 10 respectively. What do you observe? Look at C in each of the cases. You would have noticed that it is the longest side in every case. In the first case, 5 is greater than 3 and 4, 13 is greater than 5 and 12, and 10 is greater than 6 and 8. This helps us deduce something really important. In a right triangle, the hypotenuse will always be the longest side. Consider a straight line L and let A be any point not on the line. Let AB be the perpendicular from point A onto line L. Remember, point A is an external point and we have drawn a perpendicular from it to the line. Let's try to draw another line from this point to any point on the line. Say we draw one like this and call it AC. We can see that a right triangle ABC is formed, and AC is the hypotenuse. Let's zoom out a bit. Since it is a right triangle, we can use the Pythagoras Theorem. And in this triangle, we can say that AC squared is equal to AB squared plus BC squared. The square of the hypotenuse is the sum of the squares of the other two sides. Using numerical values, we had found out that the hypotenuse is always the longest side in a right triangle. Since the hypotenuse is the longest side in a right triangle, we can say that AC is greater than AB. AC is greater than AB, then it implies that AB will be less than AC. This perpendicular length is less than this length. Now say we have another line like this. Let's call it AD. Triangle ABD is a right triangle and AD will be greater than AB, which means that AB will be less than AD. No matter what line segments we consider from point A onto line L, the length of perpendicular AB will always be lesser than each of them. So the shortest distance from a point to a line will be its perpendicular distance to the line. Let's try to answer a simple question. Assume this is a floor of your house and this is a wall at the end of the floor. And we have a ladder placed like this against the wall. The length of this ladder is given as 13 meters. So this length is given as 13. Distance from the bottom of the ladder to the wall is given as 5 meters. This length will be 5 meters. Bottom of the ladder to the wall is 5 meters. We are asked to find the distance from the top of the ladder to the ground. So we have to find the length of this segment. This is 13 and this is 5 and we need to find this length. How do we find that length out? You would know that a wall is generally perpendicular to the ground. Now it gives us a clearer picture. What we have is a right triangle. Let's transpose the triangle to the right. Let's call it triangle ABC. AC will be 13 and BC will be 5. Let's zoom out and find the length of side AB. Since this is a right triangle, we can use the Pythagoras theorem and write AC squared equals AB squared plus BC squared. In this equation, we have just one unknown. AC is 13 and BC is 5. We just need to find AB. Substituting the values, we can write it as 13 squared is equal to AB squared plus 5 squared. Transposing 5 squared to the other side, we get AB squared equal to 13 squared minus 5 squared. This value can be found out, which in turn would give us this value. This equals 169 minus 25, which equals 144. We get AB squared as 144. Taking the square root on both sides, we get AB as 12 meters. So AB will equal square root of 144, which will equal 12 meters. But this is not how problems are asked. This is how problems are asked. A ladder 13 meters long is placed against a wall. Distance from the bottom of the ladder to the wall is 5 meters. Find the distance from the top of the ladder to the ground. But do not worry when you see such lengthy problems. Just read them carefully part by part. Visualize the figure and focus on how you will find the unknown. Try reading the problem and relate it to the figure we have drawn.